Okay, so this is about catalyst for ammonia synthesis. So non-transition metal-based catalyst for ammonia synthesis. By the way, my name is Peter Ngene. I'm an assistant professor at the Materials Chemistry and Catalysis Group, which is part of the Debye Institute for Nanomaterial Science, Utrecht University in the Netherlands. So basically, the motivation for the work we do here is to look for materials that can be used to achieve energy and environmental sustainability. And so basically, I work on high energy density batteries, but also energy storage material like ammonia.
Thanks, but can you try and get it in the presentation mode? We've got the slide on the right with no notes with it, so I'm sure we can just get one slide.
Oh,
please.
Is it okay now?
It went back, but we'll stick with what you've got now. Thanks.
Let me check. Just hold on. Is it better now? Can you see it? Hello?
Hello, yes, that will do. Thanks.
Okay. But it's not. Do you still see the slides?
Yes.
Yes, we can still see the slides. Can you continue, please?
Okay. Yeah. So so basically, the idea is to look at this catalyst. In this case, the particular work I'm trying to show is just a catalyst that we enable us to make ammonia at moderate temperature, and then also maybe decompose them at moderate temperature. Here, why ammonia is interesting is the fact that ammonia contains about 17% hydrogen in it, and so we can actually crack the ammonia to get the hydrogen out of from the ammonia, and then also easily make ammonia back by reacting hydrogen and nitrogen, which we can get from the atmosphere. These slides are not really going well because I cannot see myself. Okay, so but the problem about ammonia is that even though thermodynamically nitrogen and hydrogen should be able to react even at moderate conditions to give ammonia, you still need very high temperature and especially pressure to push the equilibrium to the right side, especially at a moderate condition. But with this, then which means that we have to go to very high temperature also to be able to really activate the nitrogen, especially because of the fact that because of the stable triple bond of nitrogen. So breaking this bond is a very big issue, and that is actually where most of the energy is going to. Basically, the metals that are used that have been active for this kind of reaction are transition metals, especially ruthenium. In this case, ruthenium is one of the best catalysts, and also iron mixed with some alkaline earth metal oxides. So, however, it is only recently that it was shown that actually we do know that a lot of materials can activate nitrogen at room temperature, especially something like lithium. However, it activates nitrogen strongly to make lithium nitride. So it was only recently that it was discovered that this type of material, like lithium, when you form lithium imide, lithium nitride, you can hydrogenate the lithium nitride to form lithium imide, which upon further hydrogenation goes into lithium hydride and then releasing ammonia in that case. And so our idea is to say, okay, how can we even make this to be able to produce this ammonia more moderate temperature, because in the previous work, they did show that you need also transition metals in combination with this like lithium nitride or imide to make ammonia. In this work, we look at just intercalated, just putting some of this not transition metal, but in this case, just metal hydride in graphite, confining them in graphite and trying to see if just this, the close contact with the carbon can actually enhance the performance of this metal hydride that are already known to be active anyway in combination with transition metals. Surprisingly, what we did see is, are you still seeing the slide? Because it seems not to be, hello? Hello, can you?
Yes, we can see the slides.
Okay. So then, surprisingly, what we did observe is that just putting the metal hydride in these graphene layers, confining them in the nanoporous graphite, and then decomposing them, then the lithium or sodium in this case also can go into the graphene layers. And when this metal are in the graphene layers, then it is actually active as a catalyst, even without any transition metal there. And this is what you see here. This is just basically potassium hydride that is confined in carbon. And you can see already at moderate temperature, it's 250 degrees centigrade, that it is actually active for ammonia synthesis. Actually, if you flow nitrogen and hydrogen through, that it can produce ammonia, and then the conversion or the amount of the production of ammonia increases as the temperature increases. But of course, what is remarkable about this is that this is the first time that a non-transition metal is shown to be active for the production of ammonia. Well, in view of time, I think what I'm also just going to show is that also we are not able just to do this only for, so this we try to look at the reaction mechanisms and all these, but I wouldn't bore you with this. What I just want to show is that also this type of catalysts, they are also active not only for the production of ammonia, but also you can also crack this ammonia after you have produced the ammonia, because the idea will be to react hydrogen and nitrogen, make using abundant solar energy from South Africa or from any other part of Africa. Then you make this a lot of ammonia, and then of course you can ship it to other countries where they don't have abundant sunlight. But then you have to crack back the ammonia to produce hydrogen, which will now be used in combination with fuel cells to produce electricity. And here we did also demonstrate that actually that this type of materials, these novel materials, are also not only active for the production of the ammonia itself, but also cracking of the ammonia, ammonia cracking. And what you see here is in this case, both a nickel combined together with sodium imide or potassium imide. And you did see that actually, if you flow ammonia over this catalyst, that you begin to crack them also around 350 degrees centigrade. But in this case, the pure metal hydride is not active for the cracking. We still have to combine it with other transition metal. But the good news is also, even with just nickel, which is abundant and cheap, I should say, is also active for this cracking of ammonia. I think so. That's all I want to show, that actually, yeah. So this kind of this holds promise actually for how do you call it, fast forwarding, or realizing the energy sustainability, because the most important challenge is how to store the energy that we produce renewably, because all the renewable energy sources like solar and wind, yeah, they are intermittent in nature, and storing this energy is a big challenge. So, and then doing that in the form of hydrogen is an option, but of course, hydrogen has its own challenges in terms of storage. So ammonia is seen as one of the best options to do this, and that's why there's a lot of industrial activity already taking place to make see how you can actually produce ammonia more sustainably. And I think Africa should be able to play a major role in this. So right now, most of the big contracts are being signed in Australia, but I think looking at the positioning of Africa, then I think there's a lot of advantage to we have a lot of advantage to be able to key into this. And of course, yeah, Africa is much closer to Europe. So then I think that yeah, this is something that we should be thinking about. So sorry for all the technical error, but also it's also due to the poor planning, because I only got this message this morning. I have to give this presentation, by this time. So, but good that it's successful. Thank you.